So welcome to Monday. Here's what we're going to do today. I'm going to do a little Unix tip of the day on this thing called SED, S-E-D, which is actually about this big, and I'm going to show you like that much of it. Okay. Then we'll go over the midterm answers. Then we'll talk more about sorting. So as you guys know, the latest homework assignment is out on sorting, and hopefully it's going all right for those of you who have tried it. Again, if you have any questions about it, put questions on Piazza. We are asking that you order elements from lowest to greatest, or lowest to highest. So that was one of the questions. And then, I'll show you this right now. So you guys laughed at me the other day when I mentioned something about bubble sort, and you're not allowed to use bubble sort. Turns out I'm not the only one who believes this. Take a look at this. Let's see. Oh, hang on. Okay, this was from this is when then Senator Obama was interviewed at Google, actually, a while ago.
Now, Senator, you're here at Google, and I like to think of the presidency as a job. Now, it's hard to get a job as president, and you're going through your exam. It's also hard to get a job at Google. We
True.
have questions, and we ask our candidates questions, and this one is from Larry Schumann. You guys think I'm kidding? Right here. What is the most efficient way to store a million three-bit integers?
Well,
Maybe I'm sorry. Maybe
no. I think the bubble sort would be the wrong way to go.
Come on.
So
Who told me this? What's that?
even President Obama thinks bubble sort's the wrong way to go.
We've got our spies in there.
Well, let's ask.
So I actually found this after the lecture the other day too, for what it's worth. So, anyway, turns out I'm not alone in that. Okay, let's see. Let's go on to the Unix tip of the day. So let's see, where did it go here? Here it is. We'll do the midterm right after this. So here's what SED is. It's actually it stands for Stream Editor. Okay, and what it can do is you input a bunch of like a data stream, and then you can modify it based on certain rules as you go along. Okay, so what you can actually do is, for instance, if you have a text file and the text file has a bunch of words that you want to replace, because that happens sometimes, right? And you want to replace all words that say green with all words that with the word blue, like all green with blue in a file. You can actually do this. And what this actually means is this says substitute, because that's one of the things SED does. The slash means some delimiter that says, hey, everything from this slash to the next one is what I want to check. And then the word, and then the delimiter again, and then what you're replacing it with. And then G says globally replace. So what it does is it reads individual lines, and it goes through on each line, and it finds wherever it says green, it will replace it with blue, for instance. Okay? And then this says, get the input from file 1 and send the output to file 2. All right? You don't actually have to put the file 2, it'll do it to the text screen. I'll show you that, or to the screen. I'll show you that in a second. And that will actually change it all. So let me show you what I'm talking about. Here we go. All right, there it is. Okay, I actually used the delimiter. You can pick whatever delimiter you want. I happen to pick colon instead of slash. It doesn't actually matter. As long as the colon isn't the part of the actual string, then that's fine. And this will replace, and this will take, I found a copy of Green Eggs and Ham online, right? And this will print out all of the things and says now it's blue eggs and ham, right? So you could do the same thing for any of these, let's see. I do not like green eggs and turkey. Whoops. Ham. You got to be a little careful that there's not parts of the words in there. And this there we go. I do so like green eggs. It doesn't quite rhyme as well. But anyway, Sam, I blurky or something, right? Anyway, so that's one of the things that sed will enable you to do. Now, sed actually, one of the most interesting parts about sed, and the same with grep that we've used before, is that it uses these things called regular expressions to actually make the matching. Regular expressions is like a huge topic in itself. Like I've seen like courses on regular expressions, right? But what it basically is trying to say, hey, what exactly are you looking for with wildcards and where in a string and all that? And it will actually, you can use that to replace, you can use that to be your search string. Okay, so anyway, just wanted to show you sed. If you want, there's a website here that lists lots and lots of stuff on sed and how to use it in different ways. Questions on that? Okay, all right. Let's look at the midterm exam. Okay, and hopefully everybody's gotten that back. If you haven't yet, you can go to that website, or you can just email me, and we'll get you the example. It's going to be out of 78 points. Actually, I believe it might, at this point, it might be out of 77 points based on other little mistakes I found. But let's go through some of the responses here. Okay. All right. Question 1, fairly straightforward, I thought, right? I hope you expected a question like this. Create the expand list. You should be able to expand a dynamic array. Pretty straightforward stuff. If you missed, a lot of people missed like this last line here. Okay, just pretty straightforward. There's 5 things. We've done it on like both homework assignments and lots of labs and things, so pretty straightforward. Okay, all right. Explain why inserting an element at the end of a sorted array is order 1 and why inserting at the beginning is order n. Well, you can read this up here, but at the end you don't have to move any elements, but at the beginning you have to move all of them. So straightforward question. All right, and raise your hand if you have any like comments on these too. And then this one screwed up a lot of people. So I mentioned this a couple times about why arrays are cache friendly. And some people said to me, hey, I don't even remember when you said that. Well, sorry. But they also said, and what if I didn't know what a cache was? How could I get this right? Well, if you know something about arrays, you kind of think, hey, what's the difference between arrays and other like linked lists? Well, it happens to be arrays are in order. All the elements in memory are in order, right? And when we actually index into that, we're using that benefit of the fact that they're in order. So all I really wanted you to say was, look, they're in contiguous location in order, and caches that it can store the entire array, and that's the way caches work. Caches can't store linked list data because you might have an object here pointing to another one way over here in memory, pointing to another one way back here in memory. And the way caches work, which is beyond the scope of this class, but the way caches work is they grab a whole chunk of memory at once, put them into the faster memory, and every time you access those various parts, they actually allow you to use the fast memory. Okay, so that's really all I cared about the cache part. I was just kind of seeing if you knew that arrays were stored in memory contiguously. Okay, questions on that? Okay. All right, let's see. Next question was this one. This is the part where, by the way, if you missed this question right here, if you circled this, that was also the answer to this. The question was circle all of the lines that utilize the operator equals overload. Well, this one utilizes operator equals overload, so does this one, and so does this one as well. Because what it's doing is it's copying an object it's copying the day object into another day object. And that means it has to use the equals operator to do that. Okay, so if you lost points on that, I'll give you the point back. If you lost points on that, it was my mistake in grading it. And then a number of people forgot the little ampersand here on the day list. We did not take points off for that. If you got points off from that, let me know, because I'll give you the point back there. I didn't want to make you too concerned about the actual syntax of that part of it. Because if you did this, if you left off the ampersand and then compiled this, the compiler would immediately flag it and say, hey, that's wrong. Now, should you know that that's what it should be? Yes, but I wasn't going to take points off on that one. Okay. And a number of people got this one wrong too, where they said, hey, returning the day count they're trying to return the day list at day count, but they forgot that we had just incremented that, so you needed to return the one previous. Now, comments on this question that I will take to heart for future questions. this was straight from the homework, but you could have implemented it differently. Maybe you didn't understand the way this is implemented. I think in the future I will not have questions that are this tied into the homework example, or the homeworks and the assignments. I mean, I think that's probably a bit much in terms of you could have, you didn't necessarily know that you were trying to return the right thing. I didn't explain it enough. I will take that into consideration for next time. Questions on this one? Okay, let's see. Asymptotic behavior. Most people did great on this question. Fairly straightforward. What's the asymptotic behavior of all these functions? And that was fairly straightforward. And then this one also, this was saying, what's wrong with following logic? A number of people said on this one, if you remember it, it says, look, inserting at the front of the array is order n, expanding is order n. A number of people got this kind of right, but they said the reason it's not n squared is because you don't have to expand the array every time. Well, it turns out that it's not quite that simple, because if you did have to expand the array every time, would it be order n squared? Yeah, why not? Okay. They're not nested. Yeah, I mean, the point is that it's like an order n here and then another order n. So really, at the most, it would be order 2n, not order n squared. So we took some points off of you if you had that, but not too many. Most people did fine on it. Okay. All right. This question. So here's the big one on this one. A lot of people missed this. They forgot one of two things. First of all, if you say cancel event breakfast, how do you know this one is the actual breakfast event? A lot of people forgot to say, oh, you've got to check this and see if it is, and if it's not, you have to walk to the next element and check it there. Other people forgot to do a temporary pointer, and what they did was they said, okay, they find breakfast, then they change the event list to point to lunch, and then they delete breakfast. But the problem with that is, if the only thing pointing to this right now is the event list, and you go ahead and change that to point to something else, how do you go ahead and how do you actually delete this if nothing's pointing to it anymore? So you had to be explicit about saying there's a temporary variable there. Okay. All right. And same sort of thing with the bottom one. This one, people did the same thing. Some people forgot to walk through the list. Generally, they deleted in the right order or inserted in the right order, but they forgot to do the walking through to search for the one where you need to put it. Okay. Questions? All right. Let's see. This next one. Okay, this is the one that so this was worth 6 points. This page, and I think the average was like 2.5 points or something. It was not a very good page. And here's part of the criticism I got was, hey, maybe we did cancel event wrong. That was part of the criticism. The other part of the criticism was leaving out stuff is really hard to debug. Like if something's missing and you're reading through code, like you don't know to think about that. Fair enough. Like I get that. What I suggested to a couple people was, in order to get this problem right, you have to think, okay, what do I need to do to cancel an event? And then draw a couple ideas like on your paper somewhere and say, does this work to cancel this event? Does this work to cancel a different situation? You kind of have to think of all the different situations in there. So for instance, if the event list happened to be null, well, the minute you try to do this, temp the event, you'll crash this program if that line doesn't exist, right? It's going to crash, right? Because you can't you can't find something based on a null pointer. You can't dereference that. It's not going to work, okay? So anyway, you had to know these sorts of things. And the same thing here. This case, if you were walking through this list, eventually you might end up at the end and have not found your canceled event. Like the thing to cancel might not be in your list at all. So you need to, again, remember to break out of this somehow. You could have put break and then some other logic down here, but return worked as well. Okay? And then finally, this one, this was saying, hey, look, if you're actually canceling the event, you need to set the pointer from the previous one that's next pointer to go around the one you're canceling. That's what this one's doing, except that they forgot to put the actual arrow here. Okay, because you forgot to do, they're setting the previous pointer, not the previous next pointer to that. Okay, I agree. This was a hard problem, but It was, some people did great on it, but it was definitely a hard problem. Questions on it? Okay, let's see. And then there were a couple of places where people we got extra double jeopardy points. If you think you got double jeopardy points, in other words, you got something off here that you also got above and you had both, let me know. We'll fix that. Okay, the recursion problem. You guys did great on this problem for the most part, right? A couple people had some minor things wrong in this problem, but it was actually a pretty straightforward recursion, I thought, right? You're basically subtracting from, if you want to find the remainder, you can do it using subtraction, and this is all it turns out to be. It's a two-liner, right? If a is less than b, return a, and otherwise return the remainder of a minus b and b. Work it out. Now that you know this, if you got it wrong, work it out and see that this actually works right for instance, 13.5. What happens is, for 13.5, you start out and you say, look, is 13 less than 5? No. OK, therefore, return the remainder of 13 minus 5. So then we're going to do the remainder recursively with 8 and 5. And then you're going to do another one, because 8 is not less than 5. And finally, you're going to get 3 and 5. And if 3 is less than 5, which it is, then you return 3, and that's the actual result. Okay, it's kind of it's an interesting little recursion. Most of you guys did great on it. Most of you guys did pretty well on the converting the recursive formula to a non-recursive one. A ton of people, probably like 40% of you, did the following. You didn't have a temporary in here, and you just said you looped down and you said a equals a times a. Right? And my comment on there was too many a's. Because what actually happens when you do that is let me walk through it. Right? Let's see. Do it up here. If you try to do that, what happens is you end up, got all this stuff. OK, I'll do it right here. What happens is, if you're counting down from like when you want to find 2 to the third, right? That's going to be 2 times 2 times 2, right? And so you're going to do it 3 times. So you're going to count down. So like you might count down from b, and b equals 3, right? What a lot of people said was a equals a times a. So they said a equals a times a, and a was 2, right? So they get a equals 2 times 2, which is 4. Great. Then they put the result into a. Right? So then when b equals 2, when they're counting down, now a is actually 4. Right? And what they're saying is a equals 4 times 4, not 4 times 2. Right? So that's what you wanted this one to be. You wanted a to remain 2. And so a lot of people did that. So I just took a point off for that if you didn't get that one correct. Questions on that one? OK. All right. OK, so this problem, for the most part, great. All right, let's look at the next one here. All right, whoops. There we go. Just kept going. All right, so the stacks one. This was great. Many people did very well on this one. The stack was just, if you want to reverse a string, push all the characters into the string, pop them all off into another string in that order, and you will reverse the order. There were some other interesting responses that I think got full credit as well, but that was the big one. And then this one, explain why we use circular queues instead of just dynamic arrays. The big thing I was looking for was, well, there's kind of a couple things. The big thing was wasted space, because if you're just using a dynamic array and you get to the end, you need to make more space. If you haven't used all if there's empty space behind you, then in the array, then you need to worry about that. Or that's actual wasted space. So the idea was wasted space. And then the other big one was, where did I say this here? Yeah, this is the part that I wanted you to talk about. You're enqueuing and dequeuing at roughly the same rate. Otherwise, if you're not, your queue is probably not being a very effective queue anyway. You don't have to have it about the same rate. But much like many lines in queues in general, as the line is there, people are getting taken care of and dequeued as well. Okay, so I wanted you to have that. Questions? Okay, all right. And then trees and tries. There were no tries actually, but Oh, no, there was a try. That's right, there was a try question. Sorry about the 60. Hopefully you got that right. Most people did a different algorithm than, well, some people I had no idea what algorithm you did. You created a balanced tree, and it was balanced, great. But I wanted you to use the algorithm we talked about in class, which was if you're removing a node, go to its child and go find the least element, the smallest element in its child, which happens to be 47, replace 47 at the node or replace the node you're removing with that one, and then recursively delete this one, which means 60 has to jump over to 52. So that's what this one is. Okay? A lot of people did come up with a balanced tree. I just had no idea what algorithm you were using if you didn't use one in class. Okay. All right, and then this was the wrong order. So on this one, we're trying to insert into the AVL tree. That's this one here. OK, a bunch of people did the following. They said, all right, I'm going to insert 10 down here, which is what we want to do. OK, we're inserting 10. I'm going to insert 10 down here. And then they went straight to 60 and rotated it. Right? But that's not the way the algorithm works. The algorithm works, you walk back up, and each time you check and see if you need to rotate, and only rotate the lowest most level you need to. So if 10 was here, then 20 has 0 on one side, 10 on the other, and it's doesn't need to be rotated. 30 has 1 on this side, 2 on the other, does not need to be rotated. 40, 1 on this side, 1, 2, and then 3. This is the one that needs to get rotated. So if you rotate this one, 60 doesn't. If you rotate this one, right, what you do is you bring 30 up and you move 40 down and so on, and it ends up looking like this. You never actually need to rotate 60. You only have to do one rotation the way these go anyway. Okay. All right, and then finally, the asymptotic behavior in these is really what I was looking for was the length of the word determines the asymptotic behavior, not the size of the dictionary. That was the big thing. And then you could also said something about many words have common prefixes. I was pretty lenient about grading this one, as long as you talked about the word length being the important part. Okay. All right, and then finally the bonuses. All right, most people who tried this got really close. Okay, it turns out you can go program this in C, and see what happens. This is a really tricky one actually. Turns out that signed integers go from negative maximum value to positive maximum value. And there's an odd number. There's a 0 in the middle there, right, which you need to consider. And it turns out that 0, the way they do it normally in adders in computers is they actually make it so that the 0 or the smallest negative number is 1 less in an absolute value sense than the largest positive number. So it turns out that it's 30. So a lot of people put 31. I think I gave you 1 point if you did that. But if you want more details about that, I'd be happy to explain them, or we can walk them out. This one, only a couple people got this one right. Now, I should have said that these were strings. I forgot about that. But here's what this does. I put this on here because we talked about obfuscated C. This one, all it does is this while loop. Remember, while loops continue until they get a false, like in the Boolean condition, right? So what this is doing, it says while this whole thing is true, keep doing it, right? When you set two variables equal to each other, okay, it returns the value of what the value is that you were setting them equal to. Okay, this is where the tricky part comes in. Okay, this is saying set D equal to what D is pointing to equal to what S is pointing to. Okay, and then increment both variables. If S happened to be equal to 0, you would set D equal to S, which means 0 equals 0, and that would return the value 0, which in a while loop means false. So therefore, it goes until it finds a 0 string. Now, it turns out that strings in C, not C++, but in C, character strings are a bunch of characters followed by a 0. That's how you determine where the end of it is. So kind of a tricky question. But that was obfuscated. OK. And then finally, let's see, the other three were, was the one problem with Amazon. Too few reviews can cause the best to kind of trickle to the top when it shouldn't be. I accepted a lot of different answers to that. And then we already talked about you guys who thought I was in the Army. And then this is where I was last year. Not Australia. A lot of people put Australia. I was there like 15 years ago. I love Australia, but it was a long time ago. Right? Djibouti was last year. Questions on the mid-year? If you have any questions about the grades or whatever, let me know, and we'll go through them. Yeah, Ben?
What was it out of?
It was out of 78. I think in the end it's probably going to be out of 77 because of some other mistakes I made, or maybe it's going to be out of 78, but I gave you all a bonus point anyway. I think that's what it was. Yeah?
You can put this absolute distance.
I'd be happy to put it up, sure. Yeah. Yeah, send me an email or remind me. I'll put it up there. OK, other questions on the mid-year? All right, good job overall. I think it was. I think you guys did great. OK, let's get back into sorting. OK, so we've talked about a couple different sorts already. Remember, we've talked about an insertion sort, and we've talked about a selection sort. And now we're going to talk about this thing called a merge sort. Okay, and this is one of the ones that you can do for your homework assignment. Merge sort's another comparison-based sort. Okay, and what it is it's a divide and conquer. And divide and conquer is great because we know that generally divide and conquer algorithms are a log n sort of behavior. Now, it turns out that when you're actually doing the sorting and moving it, you can't get as good as log n. You can get as good as n log n, but this one is one of the examples of that. So merge sort's a great type of sort. We also talked about shell sort, too. I forgot about that one. OK, so here's the idea of merging. At the bottom level, at the kind of base level, here's what you're doing. You're taking sorted lists and you're merging them together into another list that is now sorted. OK? And it's pretty easy to do, actually. You take 3, 5, and 11, which is sorted, and 1, 8, and 10, and you create an array that looks like this, 1, 3, 5, 8, 10, 11. You're basically independently sorting these, and it's actually very easy to do when you have them already sorted. Okay, let me show you. What you do to sort these, if they're already sorted, okay, this is before we actually get into the whole algorithm. If two arrays are already individually sorted, to merge them, it's just a matter of walking down both and comparing elements as you go along until you find the one that, and as you compare, moving the one that's lower into the array in the next position. So for instance, 3 and 1 is less, so we're going to move 1 down here, and then we're going to make the pointer to where it is in this array move over 1. Okay? So it looks like that. And then we're going to start putting it here. And the same thing goes for the next one. 3 versus 8, well, it's going to be 3, so we're going to put 3 down here and move 3 over, or move the pointer here over and the pointer here over. Same with 5 and 8. And same with 8 and 11, and 8's going to come down here. And then finally 10 and 11. And then when you get to the end, you should know that you have you have exhausted one of your arrays, right? And then all you do is copy the rest from the other array into the final. And now we've sorted those, okay? And we've taken the two that were already sorted and put them into the result that's now fully sorted, okay? And maybe this is kind of giving you a hint about how we're going to do this in kind of the divide and conquer. If we can break down our original array into halves and halves and halves and halves all the way down to where there's no more halves to take, then we can start sorting these. An array of 1 element, or 0 elements, is already sorted. Okay, that's kind of the point. It's already sorted. Okay? All right. So here's what we can do. Here's the full algorithm. Okay? Divide the unsorted, and there's actually 2 types of merge sort. We're going to be talking about what's called a top-down merge sort. There's also a bottom-up merge sort, which we're not going to worry about. Feel free to use it as one of the ones for your homework, but we're not going to do that one. But here's how it goes. You divide the unsorted list, and you can do this recursively, by the way. It's actually very easy if you do it recursively. Divide the unsorted list into n summed lists, each containing 1 element. Okay, so far so good. Now you've got all these 1 element arrays that are by default sorted, because they're the only one in the array. Then you merge them to produce new sorted sublists using the merging algorithm we just talked about, until there's only 1 sublist remaining, which is the sorted list. Okay? I'll show you the example in a sec. But any questions on the idea of that? Pretty straightforward when you think about it. Getting the recursion part working exactly right is a little tricky if you're trying to write this yourself. But really, if you can you basically take the array and break it into indexes by recursively calling half and then half and then half again. Okay, the other tricky part is when you have lists that are odd number, like one might have 3 elements and one might have 2 elements, then you end up getting, it's a little bit trickier. Not hard, but just a little trickier. Okay. All right, so here's a full example in this one. Here's the list of numbers that we're going to sort. Okay, they're unsorted. So you start breaking them in halves, right? In this case, there's 5 on one side and 4 on the other. Okay, and you keep breaking it into pieces. Okay, and then you finally get to a piece where there's just a 4 and a 0. But this one has to be broken up one more time because it's the odd one out there. Okay, and then you have them all in their individual sorted one-item lists, and you just kind of go backwards now. Okay, now we're going to end up merging 99 and 6, and 86 and 15, and 58 and 35, and 86 and 4, and 4 and 0. Well, 4 and 0 first, I guess. Right? And then we're going to merge. We're going to continue to merge up like this. Okay, these two get merged here, and they're going to end up, if you use that merging algorithm, in this order. These two end up this order, etc. Okay, and then you just keep going back up the tree, like this. All right, these two get merged like this, and this one and this one, and the arrows are kind of, just showing where they end up. And then finally, you end up merging everybody. Looks like most, yeah. And then when you have 2 sorted lists here, you end up merging them again, and you end up with one final sorted list. Okay. Question on that? Yeah. Good question. Is this in place? What do you think? This is a tough one to do in place. All right, this one's a tough, merge sort is tough to do in place for 2 reasons. If you're going to do it recursively, you're going to have to kind of have two broken up. If you're breaking this down into individual arrays, you probably can work it out such that it is. But in general, we make a new array. Each time we're breaking it down, we make a new, like this one will be a new array, and these two will be a new array. So you end up, it's not generally not in place, which is one of the issues about this. Good question. Huh?
Is there a significant memory benefit to read if you do it in place?
Is there significant memory benefit if you do something in place? For this one or in general? In general, what do you think? In general, yeah. If you have, okay, let's say you have 1 billion things that you need to sort, and it's not in place, and you need to have 1 billion extra locations to sort them. Well, now all of a sudden you've got 2 billion, memory locations you have to actually have. So it can be really bad depending on how big your data set is. A lot of times you want an in-place sort so that you don't have to worry about the extra data around. Yeah. Good question. Good question. All right. So that's merge sort there. You can do it in place. It takes more time because the elements have to be shifted. So yeah, you can do it. Generally, we don't. If you do a temporary array, it takes double this storage, which makes it fast. If you're not shifting all these elements around, it makes it very fast, which is a benefit. And this is, in general, already a fast algorithm, so you can speed it up. But it does take this double memory, so twice as much as if you're. And now, you guys don't know the era of small amounts of memory, right? Bruce and I were talking about the first computers we used were like 2 kilobytes or 4 kilobytes of memory. Like the whole computer that you could use was 4,000 locations, right? Or 2,000 locations, right? That's a small amount. Now, if any of you end up wanting to get into, say, mobile development, like with Raspberry Pis or Arduinos or that sort of thing, all of a sudden you do run into memory problems, okay, where you just have a very limited amount of memory. It's not in kilobytes anymore. It's generally megabytes, or well, depends on what you're doing. Some are as small as 32 kilobytes for these mobile devices, but you do have to think about that. So a lot of times people will think about that, and you also have to consider you do have to consider the time it takes to allocate that amount of memory as well. Yes.
Mm-hmm. Is it faster to create a second array and start copying everything over and then changing it?
Okay, if you're going to sort, it totally depends on your operating system. And the question is, if you want to make a new array to do this, is it worth it time-wise? Generally it is, as long as your memory system can allocate that amount of space. I mean, let's say you did have a huge list that you wanted to keep in memory, and it was big enough that you either didn't have enough, like twice the memory to do it. That's one thing. Your program wouldn't work at all. Or in the case where you've got, remember, you need a consecutive or a contiguous amount of memory. And if you have it, it's sometimes hard to get that contiguous amount of memory if other programs are already kind of taking chunks here and there of it. So it does depend on the operating system and the total amount that you have. Question? Can you break it into separate files? Sure, you could. Yep, absolutely. You could break it into separate files. Now, in the same time, you're going to now have even more time because getting data from files is really slow. So yeah, but you can certainly do that. In fact, if you're trying to merge huge amounts of data that won't fit in main memory, that's exactly how you would do it. Break it into smaller files and then merge individual files. Perfect. Other questions on merge sort? No? Here's the time complexity. If you do it with that extra memory and you don't worry about the amount of time it takes to create or to allocate that memory, you do get n log n for worst and best and average. Okay, so if you want a guaranteed worst, best, average n log n sort, which for comparison sorts is the best you're going to do, provably, then merge sort's a very good choice. Okay, fairly easy to program, fast, and if you can handle the extra space, no worries. Okay, good one to choose in that case. All right, other questions on merge sort before we go on to the next one? Okay, this next one is called quicksort. Now this one's a different type of algorithm, and not that different. I mean, it's another sorting algorithm. It tends to be the one that's implemented most often for fast types of sorts. Okay, in general, it's faster than other sorts. Not in every case, though. Okay, as it turns out, it has on average n log n time. Okay, but believe it or not, it actually has a worst case time of n squared, which we've already said is terrible. All right, so you do have somewhat of a trade-off with quicksort if you end up with elements that are not in a good order for quicksort to work well. We'll talk about when that becomes the case. Okay, all right. And this is kind of a fun algorithm too, and I'll show you I'll also show you the animations of it too. Okay, so quicksort, another divide and conquer. Okay, again, you're trying to break things into smaller lists, right? And recursively go through it. Okay, it's another one very similar, which is how we get the n log n behavior in the end. Okay. Here's the algorithm. All right, and we'll see a picture of this, and there's some good videos online that you can see that talk about this as well. In fact, maybe I'll show you one of the videos. It's pretty good. Here's what you do. Okay, you pick an element which we're going to call the pivot point. Okay, once you see it, you go, oh, I get it. I see what's going on here. Pick an element that's the pivot point. Okay, we'll talk about how you pick that element in a minute and why it makes a difference. And then you reorder the list so that all the elements that are before that pivot are on one side of the list, and all the elements that are after that pivot are on the other side of the list. Okay, so you just pick a pivot and then say everything bigger or less than goes on one side, everything bigger goes on the other side, and then you have what we call partitioned it. If you do it the way we're going to show you, you end up with a pivot that's in its final position. Okay, it doesn't actually ever need to be moved again. And then you recursively do the steps again to each sub-list. Okay, so you pick a pivot, have two now sub-lists that they are not sorted themselves, but they are bigger or smaller than one number. And then you do the same thing for each individual one and make it smaller and smaller and smaller. Okay? And you stop recursing when you end up with lists that are 1 or 0 because, again, they are already by default sorted. Okay? If you're not getting this, I'll show you what I mean in a sec. Okay? what we can do is there is a naive approach to this where you again have to create arrays of sublists. Okay? And this again is not in place, and it takes more memory, and it's not so great. One of the things with quicksort is because it's a recursive algorithm in general, you're going to have overheads based on the recursion, like what we've talked about with other recursive functions in general. So you can't really get away with some overhead. But we can do this one in place, okay, which I'll show you how to do it in place as well. Okay? All right. So here's the naive approach. Okay? And I'll leave it up to you to figure out how to actually program this. But here's the naive approach. Pick a pivot. In this case, we're just going to pick the leftmost item as our pivot. Why not? Okay? You pick the leftmost item and say 6. Now you're going to have the rest of, you're going to have build two more lists. One list has all the elements less than 6 in it, or equal to, and it could be the other way around. It depends on how you build it. I don't happen to have any duplicates in here. And then you have the two lists that are now greater than or less than 6, and then you do the same thing to those individual lists. Okay? So here we go. Everything less than 6 is 5, 3, and 4. Everything greater than 6 is 9 and 12. And then 6 is going to be right in the middle. Okay? Do the same thing with the individual ones. Okay? Now we say I have our pivot on 5 and our pivot on 9 for the individual sublists. Okay? Everything less than 5 goes over here. Everything greater than 5 goes over here. It happens that 5 doesn't have anything greater than it. Okay? And then same thing here. The 9 and 12, well, there's only one other element. Nothing less than 9, everything, and 12 is greater than 9. Okay? Yes?
How did you get the first list?
How did I get this list?
This, like the one and the second.
This one.
Yeah.
Okay. I pick my first pivot. Okay. And then I create two lists. I create two more lists. One.
What I mean is, do you check every element in the list and then break it up?
Oh yeah, you check it. Yes, you do. You check each element as you you check each element and then throw them into the thing. We're going to see the in-place one where you'll see how that actually goes and works. Yeah, but you do have to do that. Good question. Yeah, Eliza.
How do you determine the size of the new array?
How do you determine the size of the new array? Good question. Yeah, if you are using if you're creating your new arrays, each one has to be how big?
Well, it depends. If they were like all less than 6.
If they were all less than 6, it would have to be as big as the original, right? Yeah, so the naive approach, you do have to allocate much more space because each sublist has to be as big as the original list. Now, each sublist of here only has to be 3 long. So I mean, you gain something from it, but you're right. That's a good question. Yeah, good point. Okay. All right, so let's see. We're still down here now. Everything less than 5, greater than 5, so then 5 goes in the middle here. And then now we're going to pick this one still needs to be sorted. So we pick our pivot as 3. Everything, oops, I picked it wrong. I picked the pivot wrong. Sorry about that. Anyway, let's say that was a 4. The 3 would go here. 4 would be in the middle. And then everything is now sorted. And what you do is you merge these. You basically concatenate these back together, meaning put them all back together, and they're now in order. Okay? So that's the kind of the naive approach. Questions on that? Any more questions on that? The in-place one is kind of cool too. All right? The in-place one looks like this. Here's what you do. You still pick your pivot. Okay? And this time I put the actual index locations up here. Okay? What you do is you have a function. It's going to be a recursive function, and you're going to pass into it 2 variables. Well, 3 variables. You're going to pass in the array. You're going to pass in the starting index, and you're going to pass in the final index for that subarray. In this case, it's the whole array. So what we're going to do is pass in the array, and then 0 and 5, saying, I want you to quicksort this entire array. Okay? All right. So we pick our pivot. Here's what we do. We now have our pivot, and I'm just going to make the pivot red in this case. We are going to start one pointer on the left part of the array and the other one on the right part of the array. And we're going to start walking them towards each other. Okay? And the right one goes this way until it gets to a value that should be the left of the pivot, which is 6. So it actually starts out, and it happens to be 4, it's already left of the pivot. Right? So it's already there. And then the left one goes the other direction, goes to the right until it should be right of the pivot. So it starts here. Actually, I guess you could start it here because you know that the pivot here, because you picked that pivot, but let's say you didn't. All right. If the pivot is, if 6 should be to the left of 6, which it shouldn't, it needs to go this way until it finds one that does. And in this case, it's going to be 5. Now watch what happens when you do that. Okay. All right, the right one didn't move. The left one starts moving until it gets here. All right, we've got those two now so that 5 needs to be to the left of the pivot, and oops, did I do it backwards again? Hang on, I might have done this one backwards. Ah, there we go. No, sorry, 5 did not need to move. So you get to go one more. 9 now needs to be to the right of the pivot, 6, and 4 needs to be left of the pivot. You swap them. Okay, this is the in-place part of this. Okay, what you do is you've walked right until you've gotten to something that's less than 6. Walked left. Walked right until you get to the one that's got to be less than or greater than 6, and you swap them. Okay, so we've now swapped them. 4 and 9 got swapped. Okay, all right, and then you just repeat until those two pointers cross each other. So we keep walking this one this direction until it needs to be left of 6. In fact, it's there now. 3 needs to be left of 6. And then 4 needs to walk to 12. OK, those 12 needs to be to the right of 6. We swap those. OK. And then we've swapped that. And then now we keep doing the algorithm. Right is going to go this way. And then now they're crossing each other. And you have to do this. You have to figure the logic out of this part. But now they're crossing each other, all right? And you swap the pivot with the one that just crossed. So now we're going to swap 6 with 3. This is how this one works. And now look what we have. OK, we have 6 here. Everything to the right of 6 is greater than it. Everything to the left of 6 is less than it. Aha. That's how this, like quicksort, we already talked about that. That's how the algorithm works. And therefore, that's how this one ends up working. Okay? And what do you do now? You return the actual pivot location, 0, 1, 2, 3. Okay? You'll have to look at some actual code pieces of this, but to see how that actually works out. But remember, we had called quicksort on 0 and 5. Now we're going to recursively call quicksort on the two partitions we have, because we know we've got the location. Now we're going to call quicksort on two partitions. OK, what partition? 0 to 2, well, 0 to 3, I guess, and then 4 to 5. OK, so now remember, now we're just going to quicksort this side and quicksort this side. It's a recursive algorithm, right? And how are you going to do this one? You're going to pick a pivot of 3. I'm not going to go through the whole example here, but I've given you a link to where this whole example is actually done online. Again, the right one moves to the left until the value should be left of the pivot. The pivot is 6, so it's going to move, and then move, and then move. There is no movement in this case, because everything here is greater than 3. All right? And then they cross, so you swap the pivot and the right, but they happen to be the same one, so you don't actually do any swapping. Right? And then you keep going. And now we've got these two. And we're going to sort this one, which is trivial. It's already sorted. And you're going to sort this one. And this one's where you do quicksort on it again. Pick a pivot, and everything below 5, et cetera. You do the left and the right. OK, do you see how that's actually kind of working together to do this? I mean, it's kind of when you see it in action, you'll kind of get, oh, I get what's going on. In fact, I'll show you the video of that in a second. OK, but that's how the in-place quicksort goes. Let me do that. Let's see. What's the best animation for this one? Probably the sorting animations. Yeah, this one's the one. This one's a good one here. So let's look at quicksort. OK, so here's our algorithm. Now, this is with random, nearly sorted, reversed, and when you have a few new unique. So let's just check the random one for now. Oops. Hang on. There we go. OK. Can you see how it's doing exactly what we were saying? It's moving those two pointers close to each other. It's going too fast to actually see the swaps. But that's what it's doing. It's moving the pointers closer and closer and closer and closer, and then it's done pretty quickly. Okay? A nearly sorted list, not bad actually. This one's not too bad. Not great though, but not too bad. Okay. A reversed list gets sorted pretty quickly. Whoop, moves everybody to one side and everybody to the other because it's reversed and it automatically moves them really quickly. And the one that's the tricky one here is the few unique. Now this is the one where a number of the things that we're trying to sort are the same as each other. Okay, so you got like a lot of 4s and a lot of 5s and a lot of 7s, but not so many total. I mean the same amount total, but not the individual ones are not as many. Now watch what's happening here. This actually takes a long time to do, as it turns out. We'll talk about why in a sec. But when you have a few unique variables, this whole process degrades. Right? Anybody want to kind of guess why that's the case? Do you have a few unique ones? Why we get kind of terrible performance? Tom, what are you thinking? It's unstable. That's a good point. This can be written in a stable way, but the stability, it's not so much about the stability, but I think you're on the right track. Yeah. Yeah, you can end up picking the same, well, you won't pick the same pivot the number of times, but the same number will get picked a number of times. Yeah. And then if you pick the same one each time, you end up with a list that's always skewed towards one side, and you only gain by 1. Very good. Okay, I'll show you I'll describe what I mean in a second on here. Let's see. Let me go to the next page, and then we'll go back to that. Repeated elements can cause the list to slow down. So let's pretend that the entire list was all the same number. Okay, let's say we had a whole bunch of 4s. Okay, and we pick a 4, and that's our pivot. Well, we have to make a call whether the same numbers go on one side or the other. But if they were all the same, they would all go on either one side or the other, right? And so then you've got you've sorted 1, and you've got n minus 1. And then you pick a next pivot of the n minus 1. Well, the same exact thing happens. They all go on one side and then only 1 on the other. And each time you only get the benefit of doing one actual sorted number. So the whole process degrades. Okay? We can fix that by saying, all right, that's kind of a special case where you've got numbers that are the same, right? Instead of having 2 groups, what some clever person came up with was separate the values into 3 groups. Those that are less than, those that are greater than, and those that are the same. And then once they're the same, they're already sorted, so just do the other subgroups. Okay? Sometimes that's called quick 3 or just an improved quicksort. And that's a better way to do it with improved performance. Yes?
Couldn't you just have your quicksort not shift values that are the same? So it wouldn't pass, for example, if you're going, is this greater than that? It would always return false, so it would just keep shifting over.
Could you have it so that it ignored the ones that were the same? Exactly. The problem with that is you have to remember you've got to if you're doing this sort, remember how it works, right? You've got to find a value that's less than, you've got to find a value that's greater than, and you have to swap those, right? You have to do that swap, otherwise you'll never get the one that does need to be moved to the right place. So that's the only problem with that one. I don't think you can just ignore those because those elements won't end up swapping with the other one that needs to get swapped. That's probably the...
But those ones don't need to be swapped because they're not greater or they're not less than.
But they do need to end up on one side of the pivot or not, right? They are already on one side of the pivot. Well, not necessarily, right? Okay, so you pick 4, and then interspersed in the rest of the array is other 4s. Some of them are going to be on the one side of where the pivot ends up being. Some of them are going to be on the other side. So they do have to be swapped in some case, right? So
that can be changed depending on where you choose your pivot, right?
well, yeah, but you don't. Yeah, that's a good question. The comment was that can be changed depending on where you pick your pivot. You can't just figure out where to pick your pivot every time. That takes up too much time, right?
Pick the middle value, so just not
Yeah.
value-wise.
Okay.
Just say you got an array of 10, you just pick 5 each time.
Okay, hold on. I see what you mean, but let's just walk through this. Let me walk through the way let me walk through an example that I think will say that that's going to degrade a bit. Okay, let's say you had 4, 3, 4, 7, 4, 2, 4, right? Okay, and you pick your pivot to be 4. All right. So now, some of them are going to be to the right of where the pivot. Let's say the pivot ends up going here, right? In the end, you're going to have to add this 4, which is our pivot, kind of ending up here. Some of them are to that side of the pivot, and some of them are not. So you're going to have to, at some point, swap those. They do have to. You have to make a call about which side they are, unless you do this other. Unless you have a third list, which you say everybody else kind of goes in the middle.
What if you pick your pivot to be 7 instead of 4?
Yeah, that's fine. But how do you know that that's not? There's other 7s around. I mean, that's the point.
Once your pivot's in the middle, you don't have to shift them over anywhere.
Yes, you do. If this was the middle and that happened to be a 4, well, if I picked this one, right? Well, all the 4s have to be on this side eventually, or on that side eventually.
Can't that middle 4 just be in the middle of all the 4s?
Can't the middle 4 be all in the middle of the 4? Sure it can, but these ones have to be swapping. And what are you going to swap these ones with? I mean, each other? I don't know. If you can figure it out, awesome. If it does work out, that's great. I have not heard of that, like leaving them in place like that. But I like the way you're thinking. I mean, I like the idea of like, hey, maybe there's a better way to do it. Maybe there is. But I don't think so in this case. I'm just not sure. Yeah. Good questions, though. Very good questions. OK, let's go back one sec to talk about picking this pivot. OK, because that is kind of important. The original quicksort always picked the pivot on the left, which is the one we just picked. Okay? It always just said, hey, the original algorithm that was written up in the paper said just pick the left one, because it doesn't matter what your pivots are. Pick the left one, and you'll just be doing that. If you start with a sorted list, right? Let's say it's almost sorted, and you're always picking the leftmost value. You will always be picking a value that's less than almost all the other values. Right? And so that's not a very good case. That also degrades into n-squared behavior. Why? Because if it was already sorted, right? If it was close anyway, let's say you start out with something like that was like 2, 3, 4, 7, 6, 9, right? That's almost sorted. The first pivot, if you picked 2, right, you'd be fine. But the problem is everything else would go to the right of it, and you'd have that just one element in its own list, right? And then you go here, and the same thing. The only thing that's different, this one's already done. Everything else. So it's not a very good situation if you're just picking the one on the left. A better idea is to either pick a random location, just say randomly go through and so boop, that's it. And picking a random number, and it doesn't have to be really random, right? There are very fast algorithms for saying what's the next very random number in this group, like in random index. You can do that pretty fast, and then you just pick one, and it's just happen to be random, and then the odds are that it's not going to be degenerate in that case. Or you can say I'm going to pick the one in the middle, which is say I'm always going to pick the one right in the middle, and that might work too. The problem with that is you have to be careful. If you're dealing with numbers that are bumping up against the maximum size of whatever number type you're using, if you do this and you say, well, how do I find the middle of something? Oh, add the left side to the right side and then divide by 2. Right? Well, if you do that, sometimes you can end up overflowing the number of the actual number that you're trying to actually calculate. So it's a little careful. A better way to do it is to say left plus, subtract first, divide by 2, and then do that. That's just kind of another little thing you have to be careful about. Okay? So picking your pivot is kind of important in this case. All right. Let's look at the complexity of this. Well, in the best case, and it's a little hard to analyze this, but in the best case, time complexity is n log n, which is what we want. And in fact, as I said, many sorts use quicksort because it's a very fast sorting on average. Very fast, better than many of the other ones. Not always, but better than many of the other ones. Worst time, though, it can degrade into n squared, especially if you have lots of the same element and you're not using quick 3. Average time, n log n, which is good. The space complexity. So if you keep creating new arrays, right? If you're not doing that, you do need up to n more space, because each time you need to create more elements. Okay? And but if you do it in place, you still need log n extra space. What they're counting in this case is the recursion nature of it. That's kind of what they're counting. I think that's a little cheating, but they're counting the recursion in that case for the extra that you need. Okay? All right, that's quicksort. Yes?
Can a quick 3 be done in place?
Can a quick 3 be done in place? I believe it can, yes. I'm just not exactly sure. I haven't looked at that algorithm. Good question, Mitchell. Yeah. Anything else on quicksort? Okay. Let's see. I just showed you the quicksort there. There's some more videos there's some more videos at the end of the presentation that you can look at the other quicksort videos. But there's some good ones out there. Okay. All right. So those are the 2 other selection sorts I wanted to talk about. The next one I'm going to talk about is a completely different type of sort. Okay? This is actually, I think, a very interesting type of sort. In fact, one of my colleagues in graduate school did his whole dissertation on making this type of sort very, very efficient for parallelized computing. In other words, you have lots of different processors. This one's a great one to break up the work. Well, most of these, speaking of parallel processing, most of these divide and conquer algorithms are very good for using parallel processing, because you can do chunks on different processors, right? So like your computer right now has, maybe it's a 4-core machine or a 2-core machine, right? Well, that means that you've got 2 different processors that can independently work on stuff. And in this case, with the divide and conquer algorithms, you can set one processor to be working on half of it, the other processor to be working on the other half, and you've now made your what we call the throughput. You've sped up you've made it better. You sped up the actual calculation. Radix sort is actually a very good candidate for that, especially a specific type of radix sort where almost everything can be done independently. So it's actually pretty cool. Take a look at what we're doing here. Radix sort is going to use what we call buckets, okay, to place the elements we're working on based on what the value of a particular decimal place is. Okay? So what happens is you go through the numbers for however many decimal places there are. So if the numbers were at 3 decimal places, you would do the ones place, then the tens place, then the hundreds place. Okay? So you have to do 3 different passes. And in each pass, you sort the elements into buckets based on the value of that decimal place. And I'll show you what I mean in a second here. Okay, but it's completely different. You're not actually comparing elements at all, like the other sorts that we did. Okay, the other sorts were all comparison sorts. This one is not. Okay. I already have this one. The buckets are individual arrays, and for decimal numbers, okay, they're based on the value of the digit at that place, ones place, tens place, hundreds place. And so you need 10 different buckets for decimal numbers. Okay. All right, let me show you an example. It's a little hard to see the numbers. OK, so here's a bunch of numbers. Now, these were carefully chosen so that they didn't have any numbers above 3 in them, all right, so that it fit on the screen. But you could do this for any decimal numbers you want. Okay, but what it is in this case, we're going to have 4 buckets. Okay, and here's what we do first. We go through the list, and wherever the ones place, or the units place, is 0, that goes into the 0 bucket. Every time the ones place is a 1, like 301, that goes into the ones bucket. See how that works? Okay, and so you can see here that the bucket numbers actually go right with the digits there. But the first one's going to be 310, 130, 330, and 120 because they all have the ones place of 0. Okay, pretty straightforward, I think. Then you concatenate all of these together. In other words, you take these ones and then you put these ones next to it. So you would put 310 back here and 130 here and 1330, etc. And then 301 goes here and so on. and then you start all over, right, with the tens bucket. Okay, so now we've got, these were the first four. Notice they all end in 0, and then they all end in 1, and then they all end in 2, and they all end in 3. Okay? And you then do the same thing for the tens place. So anytime there's a 0 in the tens place, that goes in here. Every time there's a 0 in the, or a 1 in the tens place, goes in the next line, etc. Okay? Like that. 301, 201, 002, and 102. I wrote these 002 out so that you could just see the tens place, but you can use a little math to figure out if it's divisible by 10 in this case, or has a, you can figure out what the place is with the judicious use of the remainder function in general. Okay, so then now you've got everybody sorted by the tens digit, and do the same thing and repeat finally for the hundreds digit, which is here. Okay, and then the same thing. We do the 002, 013 by the 0 in the hundreds digit. Okay, straightforward. And look at this. When you concatenate these all together again, you end up with 2, 13, 23, 32, 102, 111, etc. Okay. Questions on that? I think that's kind of a neat sort, and it's different than a lot of the other sorts that we've seen before. Okay, I'll show you a video of this one, or an animation of this one that shows it in a slightly different manner. In practice, this is what I'm going to show you in a second. In practice, the bins are generally queues. And we use queues because we need a first in, first out situation. When you see the animation, you'll see how it's laid out. Okay? Time complexity is a little tricky here. The way we've been talking about time complexity for the other sorts was by basically the number of comparisons and how much time it takes to do comparisons. Because there aren't any comparisons in a radix sort, it's a different idea altogether. So it's tough to get the actual complexity. However, you can talk about it in terms of the number of digits that you actually have, because you need to pass through the array that many times based on the number of digits. And in the worst case behavior is actually order number of digits times n. Before, we were talking about comparison sorts, and we said, hey, comparison sorts only, like the best you can do is n log n. Well, look at this. We can do better than n log n for radix sort. That's great. Why don't we always use radix sort? Well, a couple reasons. Reason number one is that you do have extra overhead by doing all the comparisons to figure out what the digit itself is. And that actually takes a fair amount of time because you have to do divisions, and that takes some time. So that's a little tricky. Okay. The other one is that there is another space requirement, right? Because you have to have buckets that are each big enough to hold up to all the other digits. If you have n or d times a number of buckets, each of the size of your complexity, you can end up having a rather large extra amount of space to do this. Okay, let me show you. Hopefully this will work. The Java was being finicky before, but let me show you the video here. Here we go. Okay, not now. Yes, I want to trust. Hang on. Hang on. All right. Java's wants me this. Let's see. Okay. Whoop. There we go again. Okay. Come on, you can do it. There it is. Okay. So here's what it looks like. So this is actually modeling it like actual buckets, right? But these are actually queues. Okay. So here's what I'm going to do. I'm going to make it. You actually don't need that much of a delay on this one. But okay. So here's what it's doing. Okay. It's taking all the numbers based on their units digit and sorting them into these buckets. Okay. So all the next one's 2, so it's going to go over in 2, and the next one 9, next one's 5, etc. Okay? And then what it does is it actually bumps it up here, and this is why we need a queue. Notice they're going to come out in first order, okay? So they're going to come out in the order that they went in. Okay, and now what we're doing is we're redoing it based on the tens place now. Okay? But how do you do it? You just do it based on the order that they come out, and that's how you keep it in order. based on the previous order, generally. Okay? And that's going to do the same thing. It's going to move, after it gets done here, it's going to move them up to the top. And it's going to now do it by the hundreds place. Okay? And as I said, it's relatively quick when you do this in practice. In practice, it's very quick. The only hard part is doing the comparisons to figure out which digit, what the actual tens or hundreds digit is. Okay, and then one more, and then finally it's going to do the thousands digit on this one. And after it gets done, it's going to spit them out one more time. And did it stop? There you go. Once it gets done, it's going to spit it out one more time, and then it's going to be, if it does it in order, it will completely be in order. Okay. All right. And well, because it needs to get them back into an array in one location. So it's going to now do them all in order, right? So it's going to now put the next, and then the next one's going to come out, and the next one's going to come out, and then it'll be in array in order. Okay? So that's how the radix sort works. Okay? You can do radix sort for different number systems too. If you happen to have digits that are hexadecimal, you can do a hexadecimal radix sort, or other types of number systems. Okay? All right. So finally, you can do the radix sort we were doing was by least significant bit. In other words, in least significant decimal digit is actually what we did. In other words, the ones that matter the least, like 452, the 2 matters the least in the sense of it being less important than the 4, which is part of the 400. Like if you're talking about magnitude-wise. That's the way we sorted it. First the units place, then the hundreds place, then the units, then tens, then hundreds. If you do it the other way around, okay, if you do it by most significant bit, you end up with an interesting sort. You end up sorting lexicographically. In other words, by the order of the dictionary, right? So if you did B, D, E, cat, bat, car, sort, that sorts to what you'd imagine. If you try to do numbers in the same way, this is what this would sort to. 1 and then 10, and then 2, 3, 4, 5, 6, 7, 8, 9. The reason it comes out that way, it's as if you had it's as if the 1 was not the 1's place, but it was the 10's place, basically. Okay, and you had spaces for the other one. Okay, turns out that it sorts it not the way you'd necessarily expect it. Okay, if you do it by the most significant bit, but you can. So don't make the mistake of doing a most significant bit radix sort on your homework, because you'll probably do some of them backwards. Okay. Last minute questions on these sorts? All right, we'll see you guys in lab.